All right, line T1, we are in learning task number 2, where we're going to go and take a look at our batteries for emergency lighting and for our exit systems and unit equipment type of systems. So just pull up the pens there, and away we go. We're going to start with this, talking about what the batteries are and what we refer to them as. I don't know if you're aware of it or not, but all of our batteries are going to be classed into 2 separate classes. We have got primary batteries, and we have got secondary batteries. Does not mean that secondary batteries are worse, it's just a different style. Primary batteries are going to go and be my one-time use. In other words, it's a one-time use for these things. They have one primary purpose. Once they have fulfilled that primary purpose, they're going to be done. These are going to be ones like your little AA's and AAA's that you're going to see commonly, where we are going to go and have multiple different types of construction, a lot of our zinc base and things like that. But once we use them up, we cannot recharge them because they actually deal with a consumable that is going to be inside of there. They're always going to go and have something that is going to be a consumable that is not electrically reversible. And once that consumable is done, that's it. We can't do anything anymore. A secondary cell is going to be able to be used multiple times. Think about secondary too. You can use these things at least 2 times. We're able to go and run a secondary cell multiple times, and what it has inside of there is it has a reversible chemical reaction inside of it. We've talked before about under DC, one of the big uses for DC is electrochemical reprocessing. We use it sometimes to go and create chemical reactions or to reverse chemical reactions. In this case, what we're going to do is we are going to go and reverse chemical reactions. All of these secondary cells get a buildup, this sort of, it's almost like a plaque that builds up on top of there, but it's going to be a type of oxidization. And as it goes and builds up, it drops our voltage that we're able to go and produce out of them. But then when we go and apply DC voltage in the opposite direction, we're able to go and recombine a lot of our chemicals and reverse it. Now, they're not going to go and last for forever because slight bits of damage, irreversible damage, does get done every single time that, we discharge them and then try to recharge them. So they do have a lifespan, but they've got a really, really long lifespan before they drop below the values that, we can no longer use them at. All right, let's talk about the secondary batteries then. Now that we've defined what they are, the ones we're going to use inside of any sort of a unit equipment or exit lighting or emergency supply will have to be secondary ones. Why? Because the code itself requires that we are going to always keep these things charged up. That we need to have a system that's going to be able to go and do that. We recharge them by passing the current through in the opposite direction, which reverses the chemical reaction, and we get back to where we're going to be. Usually we're going to go and have a liquid electrolyte. Sometimes we will go and have a gelled type of electrolyte, but the bulk of them are going to be liquids. And the liquids are nice because the liquids can be flushed, they can be cleaned, they can be reprocessed and put back in. In a lot of cases, the solid parts of the battery are fine. It's the electrolyte that's going to go and carry the contaminants and can be taken back out. Do know the difference between acidic and between basic types of electrolytes. We do have some types that are going to be acids. Ones that are acids, you need to know how to go and neutralize those. You should be familiar with that term, neutralization. Really important term, particularly when it comes to some of your exams that you're going to write in the future. If you have got something that's got acid, you would go and neutralize it or cause this thing to get to a balanced pH by using a base, baking soda or something like that. Don't dump it on there like crazy person because then you get a big chemical reaction. But you have to have some way that you're going to be able to dilute and neutralize. So acids are going to be neutralized with a base. In some of our cells, we have got bases. You're going to have to go and neutralize those with an acid, usually a weak chemical like vinegar or something like that. So if you're ever working around these ones and you're wondering why there's kitchen, things that are inside of there, baking sodas or vinegars, and it's not uncommon to go and see these things inside of industrial rooms, and usually they're just going to be like big Costco-sized packs. It's not that somebody has just brought that there and forgot it or doesn't know what they're doing. That's usually there for the point of neutralizing any sort of a battery spill, if that would happen. Before you work around any secondary cells, particularly large amounts of secondary cells, make sure you familiarize yourself with what the battery construction is going to be and how you can go and neutralize that. Some batteries are going to go and be vented, where we are going to be able to go and have spills that can happen out of them. Others are going to go and be sealed so that they can be operated in pretty much any position and that there's not going to be anything that's going to be able to get out of them. Depends upon what they are. Inside of a lot of our unit equipment, we're going to be dealing with a lot of sealed units. Small sealed lead acid is probably our most common one that we have, although the lithium ion is definitely gaining some ground. We're going to talk about the three most common now. We'll start with the lead acid, which was originally called the Planté cell, and it's an old battery. We're talking from 1800s. We are going to have lead plates, not very good for you. Those lead plates are going to be bathed inside of acid, sulfuric acid and water, that they're going to be inside of there. And what happens is we get two separate types of lead plates inside of there that are going to be basically doped. It's going to be different alloys that we're going to have. And then we're going to go and get electrolysis. That's going to happen, that chemical removal of electrons from one over to the other. And as that happens, we build electrons onto a plate, and then we can go and dump them out into our external circuits that we will have. Our battery, by the way, is composed up of many cells that we are going to go and have. The term battery refers to the fact that we have got many cells that are going to be grouped together. Cells are individual voltage creating units. For a lead acid one over here, this is going to be about 2 volts that we're going to go and get per cell. So for this one over here, if I have got 3 of these elements inside of here, what you can't really see from here as much as the way that this is laid out, but what they have over here is that there's a post that they're going to have connected through this up to there. And then it's going to come from this post over to the next battery, through that battery, come up to the next one, through that battery, come up to the next one, where it's going to go out to my last terminal. In other words, we're going to be going through 3 2-volt units, which is going to go and get us to that total of 6 volts that we would have off of this type of battery. 6s, 12s, these are really common values of voltage that we are going to go and have off of our sealed, or off of, not just the sealed, but off of any type of a lead acid battery. Yeah, know what to do. You know, these things have to be neutralized with a base that we would have. There are ones that have got the absorbed glass mat, gel. You know, these are all things that are going to, instead of having a liquid electrolyte inside of here, which in these cases is going to be made up of a combination of sulfuric acid and then pure water. Okay, you have to go and use distilled water. Distillation is just heating stuff up till we evaporate. We leave all the contaminants behind. Do not ever use tap water because you don't know what the mineral content is. You know, some places, take a look at Greendale out in Chilliwack, that water is like rust red. You stick that inside there, you got iron chunks inside there, that battery is going to be shorted out internally and it's going to go blow up. You know, you have to use distilled water with that acid that you will have inside of there. If they're gelled, it's just going to be pieces of fiberglass that are going to be in between these that are going to hold them in there. And then these batteries themselves are able to be used repetitively. These are a different construction than the ones that you would have inside of a car. The ones inside of a car are designed for deep discharges, huge amounts of bulk current that they're going to go and dump out because it takes a lot of force to go and turn over the engine, particularly when those things are going to be cold. These ones over here are designed for more uniform but lighter loads. So don't interchange, you know, your automobile ones with stuff that's part of your unit equipment. Life expectancy up to 15 years, depending upon how you take care of them. These things should be recharged 6 months at minimum. You got to keep them from freezing. The freezing buckles the plates and causes short circuits inside of there. But you can go and keep these things going for a long, long time. Eventually, they do reach the point where we're going to have too much oxidization on each of these plates, and we can no longer reverse that. You got to get rid of it. If they are discharged, by the way, you need to go and recharge them every couple of months, because if not, that oxide layer, the lead rust that we have on there, that's caused by the chemical reaction inside of here, that lead rust hardens after a while. It's soft initially, but it dries out, and if it goes and dries out onto those cells, you're never going to be able to reverse it. That's why we always want to go and, you know, take these things and every 6 months minimum recharge them. If you got stuff, you know, at home, RVs or boats or things like that that have motors that you use infrequently, you're supposed to keep recharging them through the winter. Okay. Next one that we don't have a picture for, but it's going to go and be my Nicad cell that I would have. Nicad is not as commonly used at this point. It was kind of a jump in between my lithium ion and my lead acid. Lead acid was around for a long time. We went to Nicad where we started to see those things inside of cordless tools and other rechargeable places. It is an alkaline, or in other words, a base type of, electrolyte we have inside of these things. So for anything that is Nicad, you're going to be using vinegar to go and neutralize out that acid. They don't require anything other than recharging. We do not have to top up the electrolyte, the lead acid. Oftentimes we have to top up the water because it does create hydrogen while charging. So we just need to make sure that we maintain that by putting in more distilled water. Decent, a way that they work. They're not awesome. They're just kind of at this point getting old. That being said, if you have a piece of unit equipment, the charger inside of that is going to be built for the type of battery. If it's designed for lead-acid batteries, we can only recharge lead-acid batteries. If it's designed for Nicad, we can only recharge Nicad. And if it's designed for lithium-ion, we can only recharge lithium-ion. So in some cases, you will still need to go and acquire some of those Nicad batteries. All right, lithium-ion. This is the common light battery that most of you have inside of your cordless tools at this point. Lithium cobalt oxide that we are going to go and have as a positive cathode, specialty carbon as a negative anode that we are going to have. We have got a lithium salt solution inside of organic solvent. It's not inside of water, it's inside of an actual solvent, so it's an oil type base. We don't really worry about neutralization with our lithium ion. Now, there's nothing good inside of it that we want to touch, but the thing is we have far bigger dangers with lithium. Lithium reacts violently to oxygen. So if we get cracks inside of the casings, these things can go and rupture and cause fires. I don't know if you're familiar with the whole concept that you can't just mail things that have batteries inside of them, or taking anything battery powered on planes. You have to be really careful about it. What they're worried about is some of the early laptop batteries that were using lithium tended to crack when they got to a depressurized state up high. The internal pressure inside of the battery, which was manufactured down at sea level, was too high, and it would crack these things, expose the lithium, and then all of a sudden you get that violent reaction. They do have internal protection systems that are supposed to prevent fire as well as deep discharge, which harms them, but they do need to be carefully handled. Never put those down harsh. The ones that you have inside of your drills, by the way, are going to go and have inside of them, they got what is referred to as the 18650 cells. I was trying to remember this name earlier in one of the other videos, but it's our 18650 cells. They look like large AA batteries. These are all going to be placed together inside of the actual base of that tool, and then they get soldered together with little, our battery weld together with little zinc strips inside there. So when we have our drills and we accidentally drop them a little bit or crack them or something like that, what happens is that we're not affecting the actual battery. It's just an outside casing. But that's because they're ruggedized and designed for that. The ones that are going to go inside of these, in a lot of cases, are just going to be shrink-wrapped ones. You'll see them where it's going to be a couple of these. They look like RC batteries or something like that, and it's just shrink-wrapped batteries that are going to be together. Be careful with them. Don't drop them. Do not leave them rattling around loose inside of a van or anything like that as well. They do have a better discharge than what we would have from the Nicad, which is why they supplanted them. First of all, they're lighter. Secondly, we can get more cycles out of them. They got about double the capacity. Not nearly the same as our lead acid, so we do keep a lot of lead acid. Why not have a heavy lead acid battery inside of a piece of unit equipment? It's not like you're carrying it around. Inside of your hand tools, absolutely, we want to go lithium. But outside of that, lead acid is going to be fine because it is so robust. Okay, battery charging. Battery charging is going to be, once again, application specific. You cannot use the lithium ion, the Nicad, or the lead acid battery chargers on each other. You need to go and follow what the manufacturer's spec is going to go and be. You have to go to their size of battery that's going to be inside of there. These are going to go and be rectified. In a lot of cases, it's a rather coarse DC that we're going to go and put into them. You remember what we covered inside of A6, where we looked at rectifier circuits, those half-wave and full-wave rectifier circuits that we are going to go and have. What we're going to do, in a lot of cases, is we're going to have to go and take our voltage level down. Two ways we can do it. We either go down with a transformer, which would be that biphase. I don't know if you remember that one at all, but where we had that transformer and we took that thing down, and then we had a double set of windings on the other side over here, knocking that down to a biphase, and then we would go and have our two LEDs, just diodes that would be junctioned together, and then they would go out to our battery, and then this one would also go to our battery. Real simple operation that's inside of there. The transformer takes care of knocking down the value of voltage, but once again, it was cost on those transformers. The other one that we are going to go and have is going to be commonly where we are going to drop that thing down through the use of our bridge rectifier circuits. H-bridge rectifier. Whenever we have got a bridge rectifier circuit itself, that circuit is going to go and give us line values of voltage, but we can go and attenuate that. We can chop off the top. I don't know if you remember that whole thing about Zener voltage regulators. This would be where we would use a Zener voltage regulator, and we would go and have a low wattage, high wattage, low resistance resistor that we would burn off anything excess, and then we would just send a trickle current through from that over there. Resistor is commonly going to be used for current limiting because putting it backwards through the battery, it should be a limitless amount of resistance, and we don't generally use any sort of filtering. We're just putting it back into a battery. We don't care if it's janky looking. The battery is going to be fine. All we have to do is, we're just removing some of those electrons in bursts, just sending them back to where they came from. All right, that is it for our batteries. One more video out of T, and then that is the last of our emergency lighting.